So section 7.3, we're looking at the factor theorem. Now this is quite an interesting little fact because when you see where it comes from, it sort of seems so obvious that surely it can't be useful, but actually it's a very useful fact, and it works like this. If I've got a polynomial, right, so I've got something like, I don't know, x to the power of 5 or 7 to x to the power of something plus something else times x to the power of 1 less than this, and so on, right? So I've got, imagine a polynomial of some sort, plus a constant at the end of some sort, right? So x to the power of 4 plus x to the power of 3 plus something times x to the power of 2, or whatever it is. If I can factorise that, then maybe I can factorise it into a factor that, like x minus something or other times a smaller polynomial, okay? Now if I can factorise it, this expression here is exactly the same as this expression here, okay? So maybe it'll help us to have an example rather than me just waving at general polynomials. So if I say x cubed plus x squared minus 4x minus 4 is equal to x minus 2 times x squared plus 3x plus 2, okay? This thing and this thing are exactly the same. So if I put a value of x into this side, I will get the same output as if I put the same value of x into this side. If I put x equals 1 into here or x equals 1 into here, it doesn't matter, I'm going to get the same answer out, okay? Now, let's look at this side. And specifically, let's look at this bit. If I put x equal to 2, then this bit gives me 0. And I've got 0 times something, so overall, I've got 0. Okay? So if I put x equal to 2 in this side, I've got 0. That means that if I put x equal to 2 in this side, then this whole expression here is going to be 0. Now that is, in essence, that's the factor theorem. Okay? So if we've got a polynomial, and I'll call it f of x, well, if I substitute in a value p, and I get the answer 0, then x minus p is a factor of this polynomial, okay? And the other way around. If x minus p is a factor of f of x, then f of p, if I substitute p into the polynomial, then I get an answer of 0, okay? So it seems like that might not be a particularly useful idea, but just have a look at the very first example they give us. If they ask us questions like, show that x minus 2 is a factor of this polynomial, well, use algebraic division, we can do that. We can divide it into it and we can find the answer to the division and show that the remainder is 0, but that's quite a lot of work. Or we can say, well, let's use the factor theorem. If I substitute x equals 2 into this factor, then it would be 0. So if I substitute x equals 2 into here, if I get the answer 0, we must have a factor. And we do get the answer 0, and we do have a factor. And we can use that the other way around. We can show that for a different polynomial, 2 is not a factor, because I can substitute in 2 and find it's not a factor. And in fact, what we'll do quite a bit is something like this. Example 6, we've got a cubic here, and we don't have a method for factorising cubics. But if I can find one solution, and in fact, when I try it here, look, they've tried a few. They've tried f equals minus 1. That didn't work. We got an 8. We could try x equals 1. That doesn't work. We got 24. So we tried different values in here, f of 1, f of minus 1, f of 2. And eventually, we settled on f of 3. If I substitute 3 in instead of x, then I get 0. So 3 gives me a solution of 0 when I substitute it into this expression. So therefore, x minus 3 is a factor. So if I know that x minus 3 is a factor of this thing, then when I do this division, I'm going to get a remainder of 0. I'm going to get x minus 3 times a quadratic, and I do have a method for factorising a quadratic. So I can get this cubic is equal to x minus 3 times a quadratic, and that quadratic can be factorised. So x minus 3 times 2x plus 1 times x plus 3. So that's what they've done there in example 6, part A, and that's something that we can do quite a bit. And then once we've done that, we know something about this cubic. If we want to put that cubic equal to y and deal with it as a function, then we know about the roots of this function, because that is that cubic equal to 0. The roots are the solutions to these three linear terms, and so we can sketch the whole graph, right? Now, I'm not going to go into the details there because that really is getting back into previous chapters and functions and things like that, but you can perhaps see that the factor theorem seems like it's a sort of obvious fact, but when we use it the right way, it'll do all sorts of tricksy stuff for us. Probably worth mentioning example 7, not because it's particularly exciting mathematically, but because it's the sort of question they like to ask us. It tells us that this is a factor of this. Find the value of a. Well, if this is a factor of this, when I put x equal to minus 1 in this expression, I get the answer 0. So let's put x equal to minus 1 in this expression here, and we get 4 minus 3 plus a equals 0. And from that, I can work out that a has to equal minus 1. Okay? Now that's the end of the first half of this chapter. And I'd suggest that you treat that as a section on its own, section 7.1, 2 and 3, because 7.4 onwards really changes flavour and we start talking about mathematical proof. It's like 2 mini chapters rolled into one.